Welcome back to the Deep Dive. Today, we are taking an exhilarating plunge into what I think is the most advanced capability of large language models right now, reasoning.
It really is.
For years, it felt like LLMs were these incredibly sophisticated autocompleters, brilliant at generating text, brilliant at code structure, but you ask them a truly complex multi-step problem.
And that often just hit a wall.
Exactly.
And that's the classic limitation. I mean, if we look at the foundational training pipeline, the structure we used for years, it really explains why.
Okay, break that down for us.
So first, you have the massive compute step, pre-training. This just teaches the model the basic structure of language and code. It creates a model that can predict the next token, but not much more.
The vanilla autocompleter.
Precisely. Next, we use supervised fine-tuning, or SFT, to tune the model for specific tasks like, following instructions.
Right.
And then finally, there's preference tuning. This is usually RLHF, where we align the model with human standards using algorithms like PPO, making sure the output is helpful and, well, harmless.
And even with all that work, all that data, those vanilla LLMs just struggled with tasks that required real cognition-like sophisticated math, or calculating complex scenarios, or really tricky coding problems.
Because they were trained on next token prediction, not sustained step-by-step thinking.
Right.
So our mission today is to explore how we go from, say, an articulate parrot to an actual planar. We're going to define what LLM reasoning even means in a technical sense. We'll detail the benchmarks that quantify it, and then we'll uncover these groundbreaking new training methods.
Specifically with reinforcement learning, right?
Exactly. The methods that are building models that can, for the first time, truly think.
Okay, so if we want to build a model that can think, we first have to define what that thought process looks like. Where do we start?
Well, based on the source material, LLM reasoning is defined as the ability to solve a problem. And we're typically talking about a math or a coding problem that requires a multi-step reasoning process.
That's the key differentiator right there. We're talking about problems where you can't just, pull the answer from memory.
Exactly. So contrast a non-reasoning task, which is pure knowledge retrieval like, what is the course code of Stanford's Transformers and LLM class? The answer is instantly known. CME295.
No thinking required.
None. Now, a reasoning question needs calculation. It needs intermediate steps.
Like, if a bear was born in 2020 and the current year is 2025 and it spent 2 years hibernating, how old is it? The model has to sequence all those steps to get the right answer.
And that sequential approach is captured by the core strategy used, chain of thought, or COT.
Right.
So instead of just giving a single final answer, the model is encouraged to explicitly generate the step-by-step process, the whole reasoning chain, before it gives you the output.
And this started with just showing it examples, right? In-context learning.
That's right. Initially, that's all it was.
Okay, so let's unpack why this is so effective. It feels a little counterintuitive that just forcing the model to write out its homework would suddenly make it smarter.
There are two fundamental benefits. First, it acts as a decomposition engine. It forces the LLM to take a hard novel problem, one it's probably never seen fully solved before, and break it down into simpler, tractable subproblems that it has seen patterns for.
And the second reason, this is where it gets really clever, I think. It's about compute time.
Yes. Every single time the model generates a token in that reasoning chain, it performs a full forward pass calculation.
So generating, say, 1,000 reasoning tokens effectively gives the LLM a much bigger compute budget to process the query before it has to commit to an answer.
It's literally buying itself time to think.
Amazing.
What's fascinating is just how recent this thinking capability has become robust. I mean, the COT concept has been around for a bit, but models that are really optimized for true reasoning, they've only started hitting the mainstream since late 2024.
Right, things like OpenAI's O1 preview in September 2024.
Then Gemini 2.0 Flash in December and DeepSeek R1 in early 2025. This field is moving at an incredible speed.
So you, the listener, are probably already interacting with these systems, maybe in a chatbot. How can you spot if a model is actually doing this expensive, multi-step reasoning?
The key word you'll see in the user interface is usually thinking. Often it's displayed as a thought summary.
That little progress bar or label that shows up.
Exactly. When you submit a really complex query, the interface will visibly pause and it'll show that thinking label, that delay. That's the time the model is spending internally generating that hidden reasoning chain.
So wait, if the raw thought chain is hidden from the user, to keep it clean, why does the model even bother generating it? Couldn't it just figure out the final answer internally?
Well, that gets right back to the compute budget argument.
Yeah.
The generation of that raw hidden chain is the mechanism for solving the problem. It has to generate it to arrive at the correct answer.
Okay, so it's not just for show.
Not at all.
Yeah.
And it's hidden to maintain a clean user experience and, just as critically, to protect proprietary training data. You don't want your rivals training their models on your raw, very valuable machine code data.
This brings up a huge point about cost, one that affects everybody using these models. Are we, the users, paying for that invisible thinking?
Unfortunately, yes. This is a bit of a friction point we have to acknowledge. Users are charged for the full thinking tokens generated by the request, even if they only see the summarized final output.
Wow.
And those hidden tokens still occupy context window space and are billed as output tokens. This creates a really powerful commercial incentive for developers. Maximize reasoning ability while minimizing the number of tokens it takes to get there.
That efficiency equation is paramount then. But if reasoning is all about solving these novel problems, how do researchers even quantify success? You can't just use standard language metrics like BLEU or Rouget.
No, you can't. You shift entirely to deterministic, verifiable rewards. We focus on whether the answer is objectively right. The key benchmarks fall into two main categories: coding and math.
So for coding, we're talking about benchmarks like human evil, where problems have to pass verifiable test cases. Or SW bench, which is derived from actual GitHub issues. Did the model fix the bug? Did it pass the tests?
Exactly. And for math, the answer has to be parsed and matched against a ground truth. This can be anything from high-level academic challenges like AA, which is used in the U.S. Math Olympiads, down to something like GSM-8K, which is basically grade school math word problem.
Yeah, so the crucial metric isn't just simple accuracy, but this thing called pass at K. What does that actually tell us?
Pass at K is essential. It accounts for the probabilistic nature of these models. It estimates the probability that at least one of K attempts will succeed.
So if you tell a model to generate, say, K equals 10 different solutions for a coding problem, and just one of those 10 passes the tests,
Your overall attempt is a success.
that totally changes how I think about this. You're not just hoping for one right answer. You're generating a bunch of lottery tickets, and you only need one to be a winner.
And it's incredibly valuable, provided you can afford the compute to generate those multiple attempts.
Right.
And this capability requires very precise control over temperature during sampling.
Temperature controls randomness.
Exactly. If the temperature is too low, your solutions will be high quality, but they'll all be very similar. You won't get diversity, so pass at K won't improve much.
Meaning the model will probably just repeat the same wrong line of reasoning over and over.
Right. But if the temperature is too high, you get tons of diversity, but the quality just plummets because unlikely, often nonsensical, tokens get favored. The research finds this optimal range, often around 0.4 or 0.8, that balances quality with diverse solution paths.
You might also see other metrics like consensus at K, which is about which answer appears most often. But pass at K really seems to be the core strategy here.
It is, and this brings us to the core training methodology. We've established that writing these complex reasoning chains by hand for SFT data is just. It's not practical.
Right. But since math and coding tasks have that perfect, natural, verifiable reward, did it work or not, reinforcement learning is the ideal fit.
It's a perfect fit, and the RL setup uses two main rewards.
What are they?
Reward 1 is format. This just checks if the model actually produced a reasoning chain, usually by looking for specific tokens, like think and answer. Reward 2 is correctness, which verifies the final solution against the tests or the ground truth.
Okay, and for years, PPO was the gold standard for RLHF.
Yeah.
But it's become a bottleneck in this area, which is where GRPO comes in.
Yes, Group Relative Policy Optimization, released in 2024. GRPO is a real game changer because it's so elegant and simple.
So what's the difference?
Standard PPO needed a separate second model of value function to constantly estimate the advantage, which is how much better a response was than expected. This value function is hard to train, and it's a huge computational bottleneck.
And GRPO?
GRPO just throws the value function out entirely. It uses a group-based comparison. For any given prompt, it generates a group of completions, a bunch of different reasoning paths. Then it calculates the advantage of any single one by comparing its reward to the average reward of the whole group.
So it's using peer review instead of a separate estimator.
That's a great way to put it. And it simplifies the training enormously.
But even with the elegance of GRPO, researchers found this really strange and costly issue, especially in the DeepSeek R10 data. The model's performance would stabilize, but the average output length would just keep going up, sometimes up to 10,000 tokens.
Which is a huge efficiency problem, right? Especially when users are paying per token. The hypothesis traced this back to a subtle mathematical quirk inside the original GRPO loss function.
Good quirk.
The algorithm was unintentionally creating a bias against short errors.
Okay, explain that bias without hitting us with the deep math.
So think of it this way. The algorithm was punishing tokens in short, incorrect outputs much more severely than the same tokens in long, incorrect outputs.
So if the model got an answer wrong in just a few steps,
That error got a massive penalty. To minimize that penalty, the model learned a really counterintuitive behavior. When it knew it was wrong, it just preferred to ramble. It generated these huge, verbose thought chains to dilute the negative impact of the bad token across thousands of useless ones.
so it was actually incentivized to be inefficient when it failed.
Exactly. The fix was simple but crucial. Researchers modified the loss function either by removing that penalizing factor entirely, that's Dr. GRPO, or by equalizing the contributions of each token, like in DPO. This immediately stopped the length inflation for wrong answers while keeping the necessary length for correct ones.
That's fascinating.
And achieving state-of-the-art performance, like DeepSeek R1 did, required putting all of these fixes together into this complex, multi-stage training recipe.
So this isn't just about applying GRPO once, it's a whole strategic process.
It's a whole strategy designed to overcome the known flaws of machine-generated thoughts. The process begins with what they call initial alignment, or a cold start, SFT. They generate codic data using the model, but then they have humans manually rewrite and clean it
Why the human cleanup?
to fix formatting and language inconsistencies. The raw machine thoughts, while they might be accurate, often lack the structure and readability humans need. You have to teach the model how to structure its thinking, not just how to think.
Got it. Structure first, then performance.
Right. Next is the main GRPO R10 stage. This has the verifiable rewards, the format check, but they added a third reward here, a language consistency reward.
What's that for?
It checks the ratio of the target language tokens to stop the thought chains from mixing multiple languages, to keep the internal deliberation focused.
That is a clever bit of digital discipline.
Then you have the huge, large-scale SFT step. They mix a massive amount of generic, non-reasoning data with a huge set of new reasoning pairs. But crucially, this reasoning data is generated by the current high-performing model, and then it's rigorously filtered using rejection sampling.
So they're using judges or rules to make sure only the absolute best, perfect answers make it into the next training set.
Only the highest quality stuff. And finally, they return to the original RLHF goals.
Oh, okay.
The final RL alignment stage blends both data types again, but now it adds the standard alignment rewards we mentioned at the start, helpfulness and harmlessness. This ensures the reasoning powerhouse is still a safe and usable assistant.
This level of compute just sounds completely inaccessible to most developers.
Right.
I mean, what if you don't have the budget of a major lab? How do you scale this down to a mini model?
That's where distillation comes in as a really efficient alternative. Instead of making the smaller model, the student, go through all that expensive and complex RL training from scratch, the large teacher model, like R1, just generates a bunch of high-quality sample responses. And these responses include the full perfect code T sequence plus the final answer.
So the teacher does all the hard reasoning work first.
Exactly. Then the student model is just efficiently supervised, fine-tuned directly on these complete tokenized sequences. It learns the pattern of reasoning without having to do the heavy RL lifting itself.
Making reasoning accessible even on smaller, more budget-conscious models.
That's the idea.
This whole deep dive really shows us that LLM reasoning isn't magic. It's not some accidental emergent property. It's the result of a highly deliberate multi-stage training process built on these verifiable rewards and a rock-through algorithms like GRPO that intentionally force the autocompleter to act like a step-by-step planner.
That planning ability is vital, but if we connect this to the bigger picture, the next frontier,
Right.
we still face this fundamental challenge of control versus cost. The ability to dynamically control the compute budget, how much a model actually thinks for any given problem, is still a wide-open problem in research. If the system knows a problem is simple, why spend tokens generating a 100-step chain?
So if the system can assess problem difficulty on the fly, how can researchers integrate dynamic budgeting? Forcing it to think more, to stop early, to optimally balance performance and that user-facing cost. That equation, maximum thought for minimum tokens, that is absolutely the next big hurdle.
It really is. We hope you feel well informed about the complex engineering behind what can feel like simple intelligence.
Thank you for joining us for this deep dive into LLM reasoning. We'll catch you on the next one.